Every time a computer needs to find a piece of information, it faces a fundamental choice. Does it do things the simple, straightforward way? Or does it take a clever, more efficient route? Today, we're diving into that exact choice by looking at two classic algorithms, the trusty linear search versus the lightning-fast binary search. So let's get right to it. At the heart of so much of what our computers do is this one simple problem. How do you find one specific thing in a huge sea of data? Whether you're looking for a contact in your phone or a product on Amazon, the computer has to search. And how it does that search, well, that makes all the difference in the world.
All right, here's our game plan for today. First, we're going to really nail down the problem we're trying to solve. Then, we'll introduce our two main players, the brute force linear search and the divide and conquer binary search. After that, we'll put them head-to-head in a showdown of speed versus simplicity. And finally, we'll wrap it all up by figuring out how you choose the right algorithm for the job.
Let's just take a moment to appreciate the scale of this challenge. We're not talking about finding your car keys here. No, we're talking about finding one item among thousands, millions, sometimes even billions of other items. It's a massive problem.
To make this real, just picture this. You walk into a gigantic library. There are a million books, but they're not on shelves, they're not in any order. They're just in giant piles, everywhere. And you need to find one specific book. Where would you even start? You'd have to just start picking them up, one by one. That feeling of frustration? That's exactly the problem our first algorithm is built to solve.
So how do you deal with that messy, chaotic library? Well, you bring in our first contender, the linear search. You could call it the brute force method. It's not fancy, it's not elegant, but you know what? It's simple, and it always gets the job done. The name really tells you everything you need to know, right? It's linear, a straight line. It's a really simple process. You just start at the beginning of the list, and you check every single item, one after the other, until you either find what you're looking for or you hit the end.
And the process itself couldn't be more straightforward. You start at item number 1 and you ask, is this it? If the answer's no, you just shrug and move on to item number 2. How about this one? Nope. And you just keep doing that over and over again until you either get a yes or you run out of things to check. Simple as that.
Now, that simplicity, that's its superpower. It's so easy to write the code for this, and here's the big one. It works on any list. It doesn't care if it's a total mess like our library. Plus, it doesn't need any extra memory, and if your data is changing all the time with things being added and removed, linear search doesn't even blink. It just keeps on chugging along.
But, and this is a huge but, here's the catch. Its speed is what we call O of n, or big O of n. All that fancy term means is that the time it takes to search is directly tied to how big the list is. So if your list has n items, say 1,000,000, you might have to look at all million of them. And that can be painfully, horribly slow.
That need for speed brings us to our second contender. This one is the specialist. It doesn't work harder, it works smarter. Its entire philosophy is divide and conquer. This is binary search.
So unlike the one-by-one plotting of linear search, binary search makes these huge leaps. It jumps straight to the middle of the list. And with just that one single check, it can eliminate half of all the possibilities. But to pull off this amazing magic trick, it has one very, very important rule you can't break.
And here it is, the golden rule, the one non-negotiable requirement. For binary search to work its magic, the data has to be in order. It has to be sorted, alphabetically, numerically, you name it. If it's not sorted, the whole strategy just completely falls apart.
You've actually done this 1,000,000 times. Think about looking up a word in a dictionary. You don't start at the A's and flip every page, right? No way. You crack it open somewhere in the middle, you see you're in the M's, but you're looking for a word that starts with T. Instantly, you know you can ignore the entire first half of that dictionary. Gone. Then you take the second half and you do it again. You just keep splitting the problem in half, zeroing in on the answer incredibly fast.
And that amazing efficiency, that's captured by its speed, O of log n, or big O of log n. Now, just think about what that means for a second. Even if the list doubles in size, the search time only goes up by one single step. That's not just a little better than linear search, it's an absolutely massive leap in performance.
Okay, so we've met our two opponents. In one corner, we have linear search. Simple, reliable, works anywhere.
And in the other corner, binary search. A little picky, but unbelievably fast. So let's see what that speed difference actually looks like when we put them to the test. You know, it's easy to throw around terms like O of n and O of log n, but what do they really mean when the rubber hits the road? The difference in scale can be kind of hard to wrap your head around, so let's make it real. Let's use a concrete example.
Let's imagine we have a list with just over 1 million items, 2 to the power of 20, to be exact. Now let's picture the absolute worst-case scenario. The item we're looking for is the very last one we'd possibly check. How many steps would each of our algorithms take to find it?
And there it is. The difference is just mind-blowing. Our slow and steady linear search might have to make over 1 million checks, but our clever divide-and-conquer binary search, by just repeatedly cutting the problem in half, it is guaranteed to find the answer in a maximum of 20, just 20 steps. That's not a small improvement. That's a different universe of performance. So let's just boil this whole showdown down. Linear search needs zero prep work, it's super simple to code, but it's slow on big lists. Binary search, on the other hand, is wicked fast, but it demands that your data be sorted. And honestly, the code can be a little tricky to get right. Now, in the best case, where you get lucky and find the item on the very first try, they're both instant. Okay, but here comes the big twist. Looking at those numbers, you'd think binary search is always the answer, right? It's a no-brainer. Well, not so fast. Because in the real world, the theoretical best solution doesn't always win. And for smaller jobs, sometimes simpler is just plain better.
And this is such a crucial point. While binary search completely destroys linear search on huge lists, the opposite can actually be true for small ones. We're talking lists under a few hundred items or so. In those cases, linear search is often faster. Why? Well, it's because it's so simple. Binary search has more overhead. It has to do math to find the middle point and manage its boundaries. All that setup can actually take more time than it takes linear search to just quickly zip through 100 items.
So this really isn't a story about one algorithm being better than the other. It's about knowing you have two different tools in your toolbox, and it's about picking the right one for the job at hand. So here it is, your practical guide. You should probably reach for linear search when your list is pretty small, say under 500 items or so, or when the list is a jumbled mess and isn't sorted, or if it's changing all the time. But if you have a large, stable list and performance is absolutely critical, then binary search is your champion, hands down. You just have to be willing to pay that one-time cost of getting the list sorted first. And that really leaves us with one final thought. This whole trade-off, the choice between the simple brute force method that just works and the complex, elegant solution that's way faster under the right circumstances, that's not just about code, is it? So where else out there in the world do you see people making that same fundamental choice?